For today, we start for the first time with a postdoc, so we start with Nicolò De Ponti, that will talk about new results on Boozer and Cheeger inequality.
Okay, thank you, Emanuele, and thank you also to Maria for inviting me and for this opportunity. So today I want to discuss some results on these two inequalities. This is based on two different work. The first one in collaboration with Andrea Mondino, and the second one with Andrea and also Daniele, and they are now both in Oxford. So the plan of the talk is the following. I start by recalling the classical results due to Cheeger and Boozer. And here the framework is the smooth setting of Riemannian manifolds, in particular the compact Riemannian manifolds. Then our idea was, at least the starting point of our project, was to try to generalize these inequalities on possible not smooth spaces. So I will give a brief introduction to the theory of metric measure spaces and the RCD condition. And then I will present my results. So the first results are the two inequalities, the Cheeger and Boozer inequalities, obtained in collaboration with Andrea Mondino in this no-smooth setting. Then, since we have obtaining two sharp inequalities, in this last part of the talk, I want to discuss the equality case of these two inequalities, showing a rigidity result for the Boozer inequality and a no rigidity result for the Cheeger inequality. So let's start with the smooth setting. We have a Riemannian manifold. I always assume by Riemannian manifold, I mean a smooth connected Riemannian manifold without boundary. And I also assume for the moment that this is a compact Riemannian manifold. Okay, also you have compactness. You can consider, of course, the Laplace-Beltrami operator, and you see that the Laplacian is a non-negative operator, essentially self-adjoint, and the spectrum, here the compactness is important, is discrete. So you have a sequence of eigenvalues. Of course, the first eigenvalue, lambda 0, is equal to 0 because you have a constant function in the L2 space, so that they are eigenfunction. And we are interested in the first positive eigenvalue, so lambda 1. I recall here the variational characterization of this eigenvalue. You can compute it by taking the infimum of this quotient, the Rayleigh quotient, between all the smooth function with null mean. We will see that this is in variational characterization is particularly important for us. The other main ingredient for Cheeger and Boozer inequalities is the Cheeger constant of the space. It is defined in this way. So you taking again an infimum of a quotient. Now the quotient is the perimeter of a set over the volume of a set, and the infimum is taken with respect to every possible set. Okay, of course, you need some measurability assumption, or if you want, you can take even the infimum with respect set with smooth boundary. It's not important here. anyway, the infimum is well defined and okay, is a number. The important point is that we take the infimum with respect to all the possible set with at most 1/2 the total volume of the space of the Riemannian manifold. Of course, this constant is really related to the isoperimetric problem. Usually in the isoperimetric problem, you fix a volume and you ask yourself what is the set, the regularity of the set, and from my point of view, what is the constant realized by the minimum of the perimeter of all the possible set with this fixed volume. Here, we are not fixing the volume. The volume can range between 0 and 1/2 the total measure of the manifold. Okay, so the first result is due to Cheeger. He showed in the 70s that for any compact Riemannian manifold, lambda 1 is always greater or equal than h square divided by 4. So we always have a lower bound of lambda 1 in terms of the Cheeger constant. This inequality is sharp. Okay, we have two results due to Boozer. The first one is that in the class of compact Riemannian manifolds, the equality is never attained. But the inequality is sharp in the following sense. For every epsilon, there exists a smooth manifold, even a smooth surface, such that, okay, you realize the inequality, reverse inequality adding epsilon. Okay, once you have also a lower bound on the Ricci curvature of the space, Boozer realized that also a reverse inequality of lambda 1 in terms of h is achieved on a compact Riemannian manifold, and you have these results. Here I denoted by K the Ricci curvature lower bound, and for the moment K is less or equal than 0. And then with n is the dimension of the space, and Boozer proved this bound. Okay, this is not a sharp bound, and I will discuss later on this topic. The proof is based on regularity theory for the minimizer on the definition of Cheeger constant. Okay, you can see that on a compact Riemannian manifold, the Cheeger constant is realized by a set A, and you also have at our disposal some regularity theory for the minimizers. And then Boozer also used the Heinze-Karcher formula. A completely different proof of the Boozer inequality was given by Ledoux using heat semigroup techniques, and he proved another bound, okay, similar but not exactly the same. So for every compact Riemannian manifold, again with the same assumption of a bound on the Ricci curvature, we can prove that lambda 1 is less or equal than this quantity. The point here is that the proof is completely different, and we are more interested in try to generalize the approach of Ledoux in a non-smooth setting. Another remark is that, okay, they are different inequality, and you cannot say one is better than another, but an interesting point of the Ledoux inequality is that it is also dimension free. What I mean by dimension free, I mean that the right-hand side does not depend on the dimension of the space. So in some sense, once you have a rich curvature bound, for every dimension of the manifold, lambda 1 is less or equal than a function of h. Okay, so we want to generalize these inequality, these two inequalities, the Boozer one and the Cheeger one, to non-smooth, possibly non-smooth spaces. And let's see what I mean by non-smooth spaces and what is our framework. We will work with the class of metric measure space. They are spaces, they are a triple XDM, where XD is a metric space and complete and separable, and the measure is a non-negative Borel measure. These are the standard assumptions on the theory of metric measure space. For the moment, I also assume that the measure is finite. This is not a standard assumption, and is quite restrictive, but it's not restrictive for us in the sense that I put this assumption only for because it is easier to state all the result, and I'll give you more detail later for the case when the measure is infinite. So in this general class of space, we can consider a Lipschitz function, and its slope is a quantity, define it in this way. Of course, we recognize here something connected with the gradient of a function. Of course, here the space is general. We don't have a differential structure in general, but we can define this modulus of the gradient in the following way. Once you have the slope, you can use it to define the Cheeger constant and the forced eigenvalue. How we can do this? So I recall you the variational characterization of the forced eigenvalue, and now I use it as a definition of lambda 1. So our definition of lambda 1 is the infimum of the Rayleigh quotient, again, where the infimum is taken between all the possible Lipschitz function, okay, with bounded support if you want, and with null mean. So this is our definition. For the moment, I have not defined the Laplacian, but this is the definition of lambda 1. For defining the Cheeger constant, we need, okay, a volume which is easily replaced by the measure of the space, so by M, and the notion of perimeter. How can we define the perimeter on a general metric measure space? In the following way. Here, if you know the theory of BV function and the perimeter alla De Giorgi, this is the classical definition of perimeter of the set, of course, in a setting where we have only the slope of a function. So we take the infimum and the lim-infimum of this integral between all the possible sequence of Lipschitz function that are converging to the characteristic function of the set, and the convergence is in L1. This is a good notion of perimeter studied also in this general setting, And then we can define the Cheeger constant in the usual way. Again, I stress the fact that the infimum is taken between all the set with at most 1/2 the measure of the space. Okay, so nice. We have the Cheeger constant, we have lambda 1. To state Boozer, in particular the Boozer inequality, we also need a concept of Ricci curvature bound. And to define it on metric measure space, we need some deep theory here. So we start by considering the space of probability measures over the space X. Okay, also with a second moment condition, finite second moment condition. And on this space, it is known that a good distance that we can put on is the Wasserstein distance. I don't recall here the definition, but let's say if you don't know it, it's a good metric that you can put on the space of probability measures. And then we construct the following functional, the relative entropy functional, which is defined, okay, fixing the measure M, which is the measure of the space X, and then is the functional that takes another probability measures. And if this probability measure nu is absolutely continuous with respect to M, we take the density rho and compute this integral. For measures that are not absolutely continuous, we put simply the value to plus infinity. And then we have this important definition given and studied also by Lott and Villani and independently by Sturm. We say that a metric measure space, XDM, is a CDK infinity space if for any two probability measures that we can take on this space, there exists a geodesic in the Wasserstein space, so a curve on the Wasserstein space, which is a geodesic starting from mu0, with at the final time is equal to mu1, and it satisfies the following condition. This is a sort of convexity property of the entropy functional. Maybe if this is the first time that you see it, consider the case k equal to 0. So you don't have this term. And this is the standard convexity inequality on the geodesic, along the geodesic, which is what you can do on a general metric space. Okay, so we call this condition CDK infinity. CD stands for curvature dimension. So K is the bound on the curvature. Infinity is in some sense the bound on the dimension, but here we are not putting any bound on the dimension, where dimension is not a topological dimension, but in some sense an analytical one. There is also a definition of a CDKN condition, which is a bit more involved than this one, where you can also require that the space has, in some sense, a dimension strictly less than the number n. Anyway, we are more interested in the case CDK infinity condition. Okay, this is a definition, but is a good definition in a sense that we have different examples and properties. I recall only some of them. First of all, a class of example is given by weighted Riemannian manifold. By weighted Riemannian manifold, I mean a Riemannian manifold M endowed with the standard geodesic distance and with a weight measure. So we put the canonical measure, the volume measures, with a possible weight. And this space is a CDK infinity space if and only if this condition is realized. Okay, so we are taking the infimum of the standard Ricci form plus the Hessian of the weight V. In particular, if you take V equal to 0, so we are consider a standard smooth Riemannian manifold, the CDK infinity condition is realized if and only if the Ricci curvature of this manifold is greater or equal than K. So really, in this condition is a sort of generalization of the Ricci curvature lower bound. Okay, then another good property is that this condition is stable with respect to some suitable convergence of the space. So if you have a sequence of CDK infinity spaces that are converging, okay, for example, in the measured Gromov-Hausdorff convergence, which is a good notion of convergence for metric measure spaces. Also, the limit space is a CDK infinity space. In particular, you can see from this property that all the so-called Ricci limit spaces, so limits of smooth Riemannian manifold with Ricci curvature bounded from below, are CDK infinity condition. I recall just one example of these Ricci limit spaces, which is the cone. I recall it just to give you a simple, basically the simplest example of non-smooth space. In the cone you have the tip, which is a non-smooth point, but that it is included in this general framework. Of course, you can have also worst spaces in some sense with worst singularities. In this framework, we have not only Riemannian space, but also Finsler manifold. Manifold is a Finsler manifold if on every point you have a norm on the tangent space. So this class is of examples if the Ricci curvature bound, if we have Ricci curvature bound, is again CDK infinity. They are again CDK infinity spaces. Okay. So I say that we want to generalize the proof of Ledoux of the Boozer inequality. In his proof, a crucial role is played by the heat flow. So let's see how we can define the heat flow on a general metric measure space. Another functional really important is the so-called Cheeger energy, which is again defined using a similar relaxation we have seen before for the perimeter. In this situation, we are relaxing the integral of the square of the gradient of the function. So you can think to the Cheeger energy like a non-smooth version of the standard Dirichlet energy. And you know that at least in a smooth setting, the heat flow is the gradient flow, the L2 gradient flow of the Dirichlet energy. In this non-smooth setting, we define the heat flow as the gradient flow of the Cheeger energy. For doing this, we are using two crucial properties of the Cheeger energy. It is a lower semi-continuous and convex functional on L2, and also you have a lower semi-continuous and convex functional on an Hilbert space. You can consider its gradient flow. And we call the gradient flow the heat flow of the space. So in particular, we can consider the Laplacian as the generator of this semi-group. And also you have a Laplacian, you can see that the heat flow satisfies the heat equation, standard heat equation, this one. Okay, so we also have an heat flow. A problem in this class of spaces is that in general, the heat flow is not linear. This is a problem not related to the fact that we are working with possible no smooth spaces, but it is more related to the fact that we are considering also some Fiedler manifold. So we can see that on a general Fiedler manifold that is not a Riemannian manifold, the heat flow is not linear. So if we want to characterize in a better way the Riemannian space in the class of CDK infinity space, we can adapt the definition of CDK infinity space, or better, reinforce this definition, and following the approach of Ambrosio, Gigli, and Savaret, we define a new class of space, the RCD infinity spaces. Now R stands for Riemannian, and they are the class of space that are CD infinity, and also we require that the heat flow is linear. So this is a more restrictive class of spaces, but in some sense you are characterizing the Riemannian structure of these spaces. And of course, this is not only a definition, but it was also studied by different authors. In particular, the first papers are due to Ambrosio, Gigli, and Savaret, and they show that the heat flow is linear, and it also have different good properties. The condition is again stable with respect convergence of metric measure spaces, and you still have plenty example, for instance, weighted Riemannian manifolds, Ricci limit spaces. You can also take some quotients of Riemannian manifold, again, of course, with Ricci curvature bound. While Fiedler manifolds that are not Riemannian are now not anymore in the class of RCD infinity spaces. Okay. So we are ready to state our result. The first one is the Cheeger inequality. Here we have seen that for Cheeger inequality, you don't need any lower bound on the Ricci curvature. And indeed, we can prove it on a general metric measure space. Always you have lambda 1 greater or equal of h square divided by 4, so the same inequality that we have seen before. Indeed, we have adapted the original proof of Cheeger. You only need let's say some technicalities in the proof, but the idea is the same. And also really you don't need almost nothing for obtaining this inequality. Indeed, you can even drop the assumption of the separability of the space. Okay, so nice. We have the Cheeger inequality. And we also have a Boozer inequality. Okay, to state it, sorry. To state it, let's define this function, jk of t. Okay, here is not important the expression, but we have an explicit expression for this function. And then we have proved that for any metric measure space in the class of RCD K infinity condition, here K is any possible real number, you have a sort of Boozer inequality, and I will explain in the next slide while I'm putting the inequality in this, let's say, strange form. I will call it implicit Boozer inequality. But nevertheless, we can obtain some explicit Boozer inequality. So for instance, if k is equal to 0, so if in this class of space we are imposing a non-negativity of the Ricci curvature, lambda 1 is always less or equal than pi times h square. And in the case of possibly negative curvature bound, we obtain another inequality really connected to the standard Boozer and Ledoux results. So why we write it down in this way? Because the implicit bound that we have seen in the following form is sharp when k is positive. And we also have examples of equality. So for instance, on the Gaussian space, which is the standard Euclidean space with the 2 norm, and with the Gaussian measures that you see here, realize the equality in this inequality. Moreover, also in the possibly negative curvature case, we are not saying that our bound is sharp, but, indeed it is not a sharp bound, but it also improves the constants obtained by Boozer and Ledoux in the smooth setting. So we are generalizing the inequality in a more general class of spaces, and we are also obtaining a sharp inequality in the case of positive curvature, and improving the constants of the inequality in the case k less or equal than 0. Okay, here I stress the fact that we are not assuming anything about the Laplacian. So in general, lambda 1 is not an eigenvalue of the Laplacian. Again, here the problem is not that we are working on possible no smooth spaces, but even on a Riemannian manifold, if the man in general, the spectrum of the Laplacian is not discrete. It is discrete if you, for instance, have assume the compactness of the space, but in general, it's not discrete. So the Cheeger and the Boozer inequality that we have proved also without any assumption, in general, lambda 1 is only the variational, the quantity that I have defined in a variational way, let's say. If you know also in this general situation, that the Laplacian has a discrete spectrum, then lambda 1 coincide with the first positive eigenvalue. So also you have compactness of the embedding of W12 in L2. The Laplacian has discrete eigenvalues, and lambda 1 is exactly the first eigenvalue. Okay, so we have Boozer and Cheeger inequality. And what can we say about the case when the measure is infinite? Okay, both the inequalities still hold. You have simply to replace lambda 1 with lambda 0. Now we take the variational characterization of really the first eigenvalue, which is the following. And so we define lambda 0 in this way. And we also define, let's say, an analogous of the Cheeger constant for the case m of x equal to plus infinity. And here the definition is the same we have seen before. We are dropping the assumption that the measure of the set A is at most 1/2 the total measure of the space. Nevertheless, once you have replaced lambda 1 at h with lambda 0 and h0, you have again, you can prove the Cheeger inequality, which is exactly the same, and the Boozer inequality, where you can also put a 2 here. So the idea, and this also hold for the next results, is that even in the case the space has infinite measure, all our results hold, and you have simply to replace lambda 1 at h with lambda 0 and h0, and possibly the statement is a little difference with the one that we have seen, but the inequality is still hold. Okay, now we have seen the Cheeger inequality, which was already sharp. And then we have also obtained a sharp version, at least for positively curved spaces, of the Boozer inequality. Once you have a sharp inequality, there are two natural questions that you can arise. The first one is that can equality be realized in the inequality? Okay, we have already seen that the answer is yes, at least for the Boozer inequality. We have seen that equality is realized on the Gaussian space. And then you can also ask yourself, if yes, can we characterize the spaces where the equality is realized? In the class of RCDK infinity spaces, there are two main results that are known as rigidity results for some inequality. By rigidity, I really mean the characterization of the space that realize an equality, that realize the equality in an inequality. The first result is due to Gigli, Keter, and Kuada and Ota, who they proved the rigidity result of the so-called Obata inequality. So in a general RCDK infinity space, you can prove that lambda 1 is always greater or equal than k when k is positive. And they prove that equality is realized if and only if the space splits a Gaussian. I will explain what I mean by space splits a Gaussian in the next slide. Again, for spaces with k greater than 0, recently Anna proved that the equality case in the Bakri-Emmer inequality, which is another famous inequality that holds in the RCD infinity space, and also in the Gaussian isoperimetric inequality. If you have equality, then again the space splits a Gaussian. So we can see if a similar results hold also for our Boozer inequality. And together with Andrea and Daniele, we prove that this is the case. So if you have an RCD infinity spaces with k positive, and that satisfies the equality in the Boozer inequality that we have proven, then the space splits a Gaussian, which means that is isomorphic to a product space where a factor is a Gaussian factor, and the other factor is an RCD K-infinity space. So we have really another rigidity results in the class of RCD K-infinity spaces. The situation is very different for the Cheeger inequality. And okay, for stating it, I need another definition, which is the definition of isoperimetric profile. We say that a metric measure space admits an isoperimetric profile if there exists a function omega such that for every epsilon and for every Borel set with measure less or equal that this quantity, then the measure of the space is less or equal than epsilon, the perimeter of the set. This is really connected to our problem related to the Cheeger constant, because you can see from this bound, if you divide it by epsilon and by the measure of the set A, E, you obtain that the perimeter over the set, over the measure of the set, is greater or equal than 1 over epsilon. So in some sense, this definition is telling you that if the measure of the set is small, then the quotient perimeter over the measure of the set must be big. Okay, anyway, this is the definition. We know this is not our result, is a standard result of the theory, that every RCD K-infinity space with K positive or with a bound on the diameter admits an isoperimetric profile. So at least we have a class of RCD K-infinity spaces that satisfy this this condition. And then we can state our first result on the equality case, or better, non-equality case of the Cheeger inequality, in the sense that we have proved that for any RCD K-infinity space that admits an isoperimetric profile, then okay, the spectrum of the Laplacian is always discrete, so lambda 1 is really the first eigenvalue of the Laplacian, and then the inequality is always strict. So you cannot have equality in the Cheeger inequality under the assumption of an isoperimetric profile. If you drop this assumption, and in particular for space without a discrete spectrum, the equality can be realized. And actually, we have shown different examples where equality in the Cheeger inequality is achieved. For instance, two easy examples and also well-known examples are the following. And this is the first two is when the measure of the space is infinite. In the Euclidean space, it is well known that lambda 0 and also the Cheeger constant are equal to 0, so they trivially satisfies the equality. Also, it is known for the hyperbolic plane that you have equality. Here, the point is that they are not zero, the quantities, but still you can have the equality in the Cheeger inequality. Other two examples that we have shown in the paper, and these two are more involved, are the following. Equality is realized for a space with finite measure, Ricci curvature bounded from below, and with lambda 1 equal to the Cheeger constant equal to 0. And also, this example is given taking the surface of revolution of the graph of a function where the function has this behavior at infinity. Of course, it is not trivial that for this surface you have lambda 1 equal to the Cheeger constant equal to 0. You have to prove something. Another non-trivial example where equality is realized, the space has finite measure, and the first again the lambda 1 constant and the Cheeger constant are not 0, is given by, let's say, a surface with an hyperbolic metric. Okay, this is a symmetric free punctured sphere. If you don't know what it is given by putting an hyperbolic metric on some sort of surface. I do not enter here in the details of the example. So anyway, we can see very different examples where the equality in the Cheeger inequality is achieved. In particular, we have shown that we cannot expect rigidity results for the equality in the Cheeger inequality. Okay, I finished just mention some open problems. The first one is, let's say, a technical problem. If you, maybe I come back here, we have proven that the Cheeger inequality is always strict under the assumption of an isoperimetric profile. If the space that meets an isoperimetric profile in particular has a discrete spectrum, the spectrum of the Laplacian is discrete. Maybe this is the optimal assumption. So maybe you can ask yourself, is the Cheeger inequality always strict, assuming only that the spectrum of the Laplacian is discrete? We were not able to prove it, but maybe this is the optimal result. The other open problems are, let's say, some general problem of the theory of Cheeger and Boozer inequality. In particular, we have seen a Boozer inequality for RCD K-infinity spaces, but at least for stated, you need lambda 1 and the Cheeger constant, and we have seen that we can define it on every metric measure space. And then we need also for obtaining a Boozer inequality a lower bound on the Ricci curvature. We have work on the RCD class because on this class we can use the heat flow and it has many properties. But maybe one can prove in another way a Boozer inequality just for CD K-infinity spaces, so for a more general class of spaces, including also Finsler manifolds. Another problem is obtaining a sharp version of the Boozer inequality. So our sharp version of Boozer inequalities when the Ricci bound is a positive bound. For negatively curved space, this is open, and here one has also to assume an upper bound on the diameter of the space. And the last problem that I want to mention is obtaining a Boozer inequality for RCD or CD spaces, not for the two eigenvalues, so the eigenvalue of the standard Laplacian, but for P eigenvalues. So the idea is trying to obtain an inequality where lambda P, let's say, cioè the first eigenvalue of the P Laplacian is less or equal than a function of the Cheeger constant of the space. We know that this is true on a smooth Riemannian manifold, but it is completely open for RCD or CD spaces. And okay, I conclude here. Thank you for your attention.
Thank you, Nicolò, for your seminar. Now it's a moment, if there are the moment for questions. If somebody has a question, you can unmute himself and ask a question. Okay, it doesn't seem that there are any questions. So I want to say that for keep track of the timetable for the next Friday, because we have to decide to do it in the morning or in the afternoon. I will call Giorgio will write to you also. And nothing. We thank Nicolò again. Thank you, Nicolò, for today.
Thank you.
Thank you. Bye.
Okay, bye.
Thank you. Bye.
Maria, stop.
Ciao, buon weekend.
Buon weekend a tutti.